Welcome to this coding walkthrough. In this session, we will explore problem number 471, encode string with shortest length. This problem challenges us to effectively encode a string using the shortest possible representation, leveraging patterns and compressions. Let's dive in and break it down step by step. This problem focuses on encoding a given string to achieve the shortest possible length. The encoding format is defined as k, encoded_string, where the substring inside the brackets is repeated exactly k times. For example, the string AAA could potentially be represented as 3a. However, the goal is to ensure that the encoded string is shorter than the original. If there are multiple encodings of the same length, any valid one can be returned. The input will always be a non-empty string containing only lowercase English letters, and the output should be the shortest encoded version of the string, adhering to the specified format. To illustrate, consider the first example. The input string is AAA. While it can be encoded as 3a, the encoded version would have a length of 5 characters, which is longer than the original. Therefore, the shortest encoded version is simply the original string itself, AAA. In the next example, the input is AAAAA. Here, the string can be encoded as 5a, which results in an encoded string of 4 characters. This is shorter than the original string's length of 5 characters, so 5a is the optimal result. In a similar way, the input AAAAAA can be encoded as 10a, which has a length of 6 characters. This is significantly shorter than the original string length of 10, making 10a the optimal encoding. Another interesting case is the string abcapped. By identifying patterns, we see that it can be encoded as 2ABCD, which has a length of 8 characters. This is shorter than the original string's length of 9 characters, so the encoded string 2ABCD is the best option. For a more complex example, take the input string ababcapkabak. By analyzing the repeated patterns, we find that it can be encoded as 2ababak, which has a length of 12 characters. This is much shorter than the original string's length of 18 characters, making 2ababak the optimal encoded representation. These examples demonstrate how the encoding rule can effectively reduce the length of strings with repetitive patterns. To handle edge cases, it's important to note that if the input string has no repeating substrings, the output should simply be the original string. For instance, the string ABC would remain unchanged. Additionally, for very small strings, such as those with a length of 1 or 2, encoding is not practical since the encoded version would always be longer. Finally, the function should also consider cases with nested patterns. For example, the string ababab can be encoded as 2ab, which demonstrates the importance of identifying optimal encodings even in more complex scenarios. To solve the problem of encoding a string with the shortest length, we need to think about how to represent repeating patterns efficiently. The goal is to use a format like k, encoded_string, where encoded_string is a substring repeated k times, and the overall length of the encoded string is minimized. One approach we can consider is the brute force method, which involves exhaustive substring checking. The key idea here is to examine every possible substring of the input string and determine if it can be represented as a repeated pattern. For example, if a substring sub repeats k times to form part of the input, we can encode it as k sub. Take the string ababab, which can be represented as 3ab. While this method is straightforward to implement, it has significant drawbacks. Generating and testing all possible substrings is computationally expensive, especially for longer strings, making this approach inefficient in terms of time complexity. A more efficient solution involves using dynamic programming, or DP. This approach breaks the problem into smaller, overlapping subproblems and solves them systematically. We define dpij as the shortest encoded string for the substring sij plus 1. The goal is to compute this value for all possible substrings by checking all potential partitions within the substring. Now, the key observation here is that if a substring can be represented as k, encoded_string, it must be divisible into repeating segments. For example, to determine whether sij plus 1 can be encoded, we check if it's formed by concatenating a smaller substring multiple times. Using recursion with memoization, we calculate the shortest encoding for each part and combine the results to find the global minimum. The DP algorithm starts by initializing DP, I, J, with the substring itself as the default form. Then, for every possible partition of the substring, it computes the encoded length using the DP states of the two parts. Finally, it evaluates whether the entire substring can be represented as K, encoded_string, updating DP, I, J, if this new encoding is shorter. This method significantly reduces redundant calculations, making it much more efficient than brute force. However, it is a bit more complex to implement due to the recursive structure and memoization. Another approach to consider is a heuristic-based method for string compression. This technique uses a greedy strategy to identify and compress repeating patterns without explicitly relying on dynamic programming. While simpler and faster to implement in certain scenarios, it does have limitations. The main drawback is that it does not guarantee the shortest possible encoding, which can lead to suboptimal results. After evaluating these methods, the dynamic programming approach emerges as the most robust and efficient strategy for this problem. By leveraging the overlapping subproblems and using memoization, DP minimizes redundant calculations and ensures that the shortest encoding is achieved. Brute force, while conceptually simple, is computationally impractical for larger strings. Similarly, heuristic-based solutions trade off optimality for simplicity and speed, which isn't ideal when the shortest encoding is the objective. The DP approach stands out because it systematically explores all possible partitions to guarantee optimality. With a time complexity of approximately n cubed, it strikes a balance between efficiency and correctness. Additionally, it handles challenging cases like strings without repeating patterns or those with nested repeats. For these reasons, dynamic programming is the best choice for solving this problem effectively. To solve the problem of encoding a string with the shortest possible length, we rely on dynamic programming to systematically evaluate and store optimal solutions for substrings of various lengths. First, we initialize our variables. Let's define n as the length of the input string s. We create a dynamic programming table called dp, where dp, I, j, will represent the shortest encoded string for the substring s, I, j plus 1. As a starting point, we initialize each dp, I, j, with the substring s, I, j plus 1 itself. This is because, in the worst-case scenario, the substring cannot be compressed further. Next, we iterate over all possible lengths of substrings, denoted as L, ranging from 1 to n. For each specific length, we slide a window across the string to evaluate all substrings of that length, preparing the dp table for further computations. The next step is to evaluate each substring s, I, j plus 1, by attempting to split it into two smaller substrings at every possible midpoint k, where I equals k less than j. By combining the results of dp, I, k, and dp, k plus 1, j, we determine if a shorter encoding can be achieved. If so, we update dp, I, j, with the shorter value between its current value and the newly combined result. Additionally, we check if the substring s, I, j plus 1, consists of a repeating pattern. For instance, if the substring can be expressed as k** pattern, where pattern is a smaller substring that repeats k times, we replace it with the encoded form k, pattern. To identify such repeating patterns, we divide the length of the substring by potential pattern lengths and verify if the substring is composed of multiple copies of the same pattern. If the encoded representation k, pattern, is shorter than the current value in dp, I, j, we update it. Once all substrings have been evaluated, the final result for the entire string is stored in dp, 0, and 1. This algorithm is built upon a few key insights. First, dynamic programming allows us to break the problem into smaller subproblems and combine their results efficiently. By storing intermediate solutions in the dp table, we avoid redundant computations. Second, recognizing repeating patterns in substrings is critical for compression. For example, the substring ababab can be represented as 3, ab, which is much shorter. Finally, this approach prioritizes efficiency by systematically exploring only the necessary combinations instead of brute-forcing all possibilities. The main data structure used here is the dynamic programming table dp, which is a 2D array. Each cell dp, I, j, stores the shortest encoded string for the substring s, I, j plus 1. The size of this table is nxn, where n is the length of the input string. This structure enables the algorithm to efficiently store and reuse results across overlapping subproblems. Now, let's analyze the complexity of this algorithm. The time complexity is O(n) cubed. This comes from the fact that there are O(n) squared substrings to evaluate, and for each substring, we check all possible splits and potential repeating patterns, which takes O(n) in the worst case. The space complexity, on the other hand, is O(n) squared, as the DP table requires storage for every possible substring combination. To better understand the process, let's walk through an example with the input string s equals ababab. During initialization, each cell in the DP table is filled with the corresponding substring. For instance, DP0, 0 is initialized to A, DP1, 1 to B, and so on. Next, we consider substrings of length 2. For example, S0:1 equals AB cannot be compressed further, so DP0, 1 remains AB. Similarly, for S1:2 equals BA, no compression is possible, so DP1, 2 is also BA. For substrings of length 3, such as S0:2 equals ABA, no compression is possible, leaving DP0, 2 as ABA. However, when we move to longer substrings, such as S0:5 equals ababab, we identify a repeating pattern. Here, the substring consists of the pattern AB repeated 3 times. This allows us to compress it into the encoded form 3 AB. Consequently, we update DP0, 5 with this shorter representation. At the end of the process, the shortest encoding for the entire string is stored in DP0, 5, which in this case is 3 AB. This demonstrates how dynamic programming and pattern recognition work together to achieve optimal compression. This solution uses dynamic programming to encode a string into its shortest possible length. The encode function takes the input string s and initializes a DP table DP where DP, I, j, represents the shortest encoded form of the substring s, I, j plus 1. First, we initialize DP to store the substrings themselves, since the uncompressed form is always a valid starting point. We then iterate through all possible substring lengths from 1 to n. For each length, we calculate substrings starting at index I and ending at j. For every substring, we consider 2 key possibilities. 1. Splitting the substring into 2 parts at every possible position k and combining their compressed forms. If the combined length is shorter, we update DP, I, j. 2. Checking if the substring is composed of repeated patterns. For this, we test all possible pattern lengths k and verify if repeating the pattern forms the substring. If so, we calculate the encoded form x, y, where x is the repeat count and y is the encoded form of the pattern. If this form is shorter, we update DP, I, j. Finally, the result for the entire string is stored in DP, 0, and 1. This approach ensures that all possible encodings are considered, and the shortest one is selected. The time complexity is approximately O(n) cubed, due to the nested loops and substring checks, making it efficient for moderate input sizes. Here, we begin by importing the necessary Java utilities and defining our solution class, which contains the encode method. This method takes a string s as input and aims to return its encoded version with the shortest length. First, we compute the length of the string s and initialize a 2-dimensional array DP to store all possible encodings for substrings of s. The DP array is of size nxn, where n is the length of the string. Each entry DP, I, j, will eventually hold the shortest encoded representation of the substring from index I to j. Initially, we fill this array with empty strings to ensure all entries are properly initialized. Next, we start filling the DP table. We iterate over all possible lengths of substrings, from 1 to n. For each substring length, we compute its starting and ending indices, denoted by I and j. The substring itself is retrieved using s.substring, I, j plus 1, and as a default, we assume the shortest encoding for the substring is simply the substring itself. Now, we check for all possible partitions of the substring. This is done by splitting the substring at an intermediate index k and combining the encodings of the 2 resulting parts. If the combined length of the encoded parts is shorter than the current value in DP, I, j, we update it with the new, shorter encoding. Additionally, we check if the current substring can be represented as a repeated pattern. For this, we iterate through all potential lengths of the repeating unit, denoted by k. If the length of the substring is divisible by k, we extract the first k characters as the candidate repeating unit. We then check if repeating this unit the required number of times recreates the original substring. If it does, we construct an encoded representation of the form number of repetitions, encoded repeating unit. For example, a substring like AAAA might be encoded as 4a. If the length of this encoded string is shorter than the current value in dp, I, j, we update dp, I, j, with this new encoding. By iterating through all possible partitions and repeating patterns in increasing order of substring lengths, we ensure that by the end of the process, dp, 0, and 1, contains the shortest encoding for the entire string. Finally, we return this value as the result of the encode method. To solve the problem of encoding a string with the shortest length, we use a dynamic programming approach. Let's start with an example where the input string is AAAA. First, we initialize the length of the string, n, to 5. We then create a 2D list, dp, of size nxn, where dp, I, j, will eventually store the shortest encoded version of the substring from index I to j in the string. Initially, all entries in dp are empty strings. Next, for substrings of length 1, each character is its own encoding. For example, dp, 0, 0, is a, dp, 1, 1, is a, and so on. This fills the diagonal of the dp table with the individual characters of the string. After that, we start processing longer substrings. For substrings of length 2, such as s, 0:2, equals aa, we check if any split results in a shorter encoding. Since no split helps in this case, we check for repeated patterns. Here, a is repeated twice, so we encode the substring as 2a, and update dp, 0, 1, accordingly. The same logic applies to other substrings of length 2, such as s, 1:3, and s, 2:4, resulting in their encoded versions being stored in the dp table. Now we progress to substrings of greater lengths. For the full string s, 0:5, equals AAAA, we again check splits but find that no split reduces the length. Next, we check for repeated patterns. Since the substring consists of the character a repeated 5 times, we encode it as 5a, and store this result in dp, 0, 4. At this stage, the shortest encoding for the entire string is found to be 5a. Moving on to a new example with the input string abcapped, we reinitialize n to 9 and create a new dp table of size 9x9, initialized with empty strings. As before, we start by processing substrings of length 1, where each character is its own encoding. For instance, dp, 0, 0, is a, dp, 1, 1, is a, and so on. This completes the initialization and setup for the new example. Next, we proceed to process substrings of increasing lengths for the string abcapped. For substrings of length 2, we consider cases like s, 0:2, equals aa, which can be encoded as 2a. For s, 2:4, equals bc, no encoding is possible, so it remains bc. This process continues for all substrings of length 2. Then, for length 4, consider s, 0:4, equals aabc. Since no simple encoding is evident, we check for splits. Splitting at k equals 1, we combine dp, 0, 1, and dp, 2, 3, resulting in 2a, bc. This becomes the optimal encoding for dp, 0, 3. For length 8, take the substring s, 0:8, equals abcapped. Here, we recognize that the pattern aabc repeats twice, allowing us to encode it as 2aabc. This is stored as the optimal result in dp, 0, 7. Finally, for the full string s, 0:9, equals abcapped, no further encoding is possible, so the output remains abcapped. In the last example, we consider the input string abcap. After initializing the length of the string, n, to 12 and setting up the dp table, we begin processing substrings. For substrings of length 3, such as s, 0:3, equals abc, no shorter encoding is possible, so it remains abc. For substrings of length 6, like s, 0:6, equals abcap, we observe that abc repeats twice, allowing us to encode it as 2abc. Finally, for the full string s, 0:12, equals abcap, the pattern abc is repeated 4 times, so we encode it as 4abc. This becomes the final result for the example. The key insights from this approach include leveraging dynamic programming to solve overlapping subproblems, checking all possible splits and repeated patterns for each substring, and updating the DP table only when a shorter encoding is found. This ensures that we achieve the shortest possible encoding for the given input string. To analyze the time complexity of our solution, we start by examining the three primary loops in the algorithm. The outermost loop iterates over possible substring lengths, ranging from 1 to n. Since each length is considered once, this loop contributes n iterations. Next, for each substring length, we use an inner loop to iterate over all possible start indices, ensuring that the substrings formed match the current length. The number of such iterations decreases as the length increases, but the total contribution from this loop across all lengths sums to approximately n squared. Finally, for each substring defined by its start and end indices, we consider all possible partition points between the start and end. This involves an additional loop that runs proportional to the length of the substring, contributing n operations in the worst case. Together, these loops result in n squared, n, or n cubed operations overall. In addition to the loops, we also need to account for the operations performed within them. For each substring, the algorithm checks for repeated patterns by examining potential repetitions up to the length of the substring. This adds another layer of complexity proportional to n for each j pair. Since there are n squared such pairs in total, checking repeated patterns contributes n cubed operations. When combined with the time required for partitioning, the overall complexity remains n cubed. This ensures that even when every substring is analyzed thoroughly, the time complexity does not exceed n cubed. Breaking it down step by step, the outer loop, the start-end loop, the partitioning, and the repeated pattern checks all scale consistently within this cubic time bound. Now let's consider the space complexity of the solution. The primary contributor to space usage is the dynamic programming table, or DP table, which is a 2D array of size nxn. Each cell in this table stores the shortest encoded string for a specific substring of the input, meaning the space required for the DP table is n squared. In addition to the DP table, the algorithm uses temporary variables like substring, repeat_sub, and encoded during the computation. These variables store strings of at most length n, requiring n space. However, since n is negligible when compared to n squared, the overall space complexity is dominated by the DP table, giving us a total space complexity of n squared. To better understand the algorithm's performance, let's analyze it under different scenarios. In the best case, when the string has no repeated patterns, such as A, B, C, D, E, F, the algorithm still evaluates all substrings to confirm that no compression is possible. This means the time complexity remains n cubed, even in the best case. For the average case, with randomly structured strings, the complexity doesn't improve significantly because the algorithm still examines all substrings, checks for repeated patterns, and evaluates partitions. This consistent, exhaustive approach keeps the complexity at n cubed. In the worst case, where the string contains many repeated patterns, such as a, the algorithm intensively checks for repetitions and partitions. Even here, the overall complexity stays n cubed, because the structure of the loops and operations does not change. Comparing the dynamic programming solution to a naive approach provides valuable context. A brute force method would involve generating all possible encodings of the string and selecting the shortest one. This approach would quickly become infeasible, as the number of ways to split and encode a string grows exponentially with its length. For such a method, the time complexity could exceed 2 to the power of n. In contrast, the dynamic programming approach avoids redundant computations by storing intermediate results in a DP table, reducing the complexity to n cubed. While this is a significant improvement, there is still room for optimization. For example, memoization or limiting the range of repeated pattern checks could reduce runtime further in practical applications. Finally, let's solidify our understanding by proving the big O complexity. The n cubed time complexity arises from the structure of the algorithm. The outermost loop iterates over substring lengths, contributing n. The inner loop, which evaluates all possible start and end indices, j, involves n squared iterations in total. For each pair of indices, the innermost operations, partitioning and checking for repeated patterns, require O, n, work. Multiplying these together gives O, n, asterisk O, n squared, asterisk O, n, which simplifies to O, n cubed. On the space complexity side, the DP table stores the shortest encoding for each substring pair, I, j, requiring O, n squared, space. Since no other operations require significant additional memory, the space complexity is conclusively O, n squared. When solving this problem, there are a few common mistakes to watch out for. One is not handling overlapping patterns correctly. For instance, if the string is ababab, an incorrect encoding might be 3ab, when the optimal encoding is actually 2abab. This happens because larger repeated patterns are missed when only smaller ones are considered. Another mistake is skipping substring compression at all levels. It's important to check for repetitive patterns not just at the full string level but also within smaller substrings. Smaller substrings might compress better when combined, so neglecting this can lead to suboptimal results. Lastly, inefficient recursion without memoization is a critical pitfall. If previously computed results for substrings aren't stored, the algorithm ends up performing redundant calculations, which significantly slows down runtime, especially for strings with overlapping subproblems. Memoization is key to improving efficiency here. Another common issue is the incorrect handling of edge cases. For example, strings without any repetition, like ABCDF, or strings with highly repetitive characters, such as AAAA, can trip up algorithms. Encoding non-repetitive strings as something like one string, or failing to simplify repetitive strings can lead to errors. Additionally, assuming that only contiguous repeats matter is another mistake. Patterns don't always appear in a neat, contiguous way. Overlooking non-contiguous patterns can cause the algorithm to produce suboptimal results. It's important to design the solution flexibly to account for these scenarios and handle edge cases carefully.